Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Fei Dai with us today. Hi, Fei.
Hi, everyone. Hi, Frank.
Thank you very much for agreeing to talk about your very awesome AJ article coming up here. Very nice.
Yeah, thanks for having me. Really excited to share this system with everyone.
Yeah, it's a wild one. It's very cool. Fei, where are you located at? What's your geolocation?
Currently a postdoc at Caltech,
Very cool.
Astrophysics department here, been in Caltech for 4 years. So I'm currently a NASA Sagan Fellow here. Yeah, so in general, my research is exoplanets, looking at their composition, their mass loss, their orbital architecture. This new system we are looking at actually presents a really unique orbital architecture, a resonant chain. Really excited to share it with everyone.
Cool. Yeah. Well, in that case, on this March 8th of 2023, let's get into this very awesome article. This is an AJR, and it's open access, people. You can go get a copy for free. Go grab one. TOI 1136 is a young coplanar aligned planetary system in a pristine resonant chain. And Fei, take us away.
Thanks, Frank. Yeah, first of all, I would like to acknowledge my collaborators. You can see there's a long list of people, including my close collaborators who actually work on the system, and also the test team who actually contributed to making sure text works. And they were the first to identify the system. Cool. And also collaborators who are working on ground-based follow-up of the system using the large telescopes.
Nice.
On the ground, radial velocity, spectroscopy follow-up, things like that.
Very cool. Very cool. Thanks. Big
group
here. Okay.
Yeah. So before we examine the system in detail, let me just give some background.
Okay.
So a key prediction of modern planet formation theory is that planets migrate as they grow in a polar planetary disk. And this has been realized decades ago. The main reason is as the planet grows, its mass increases and the planet can back react on the disk. Okay. So the gravitational interaction between the planet and the disk usually shows up as link back resonance or co-rotation torque. I won't go into the detail, but the net effect is usually for the planet to migrate toward the central star. Right. Okay. Now, if you are forming multiple planets simultaneously, then all the planets tend to migrate. And the heavier planet, since they impose a strong influence on the disk, tend to migrate faster. Makes sense. Okay. So this leads to a differential migration between the planets and allowing the planet to sample or sweep through a range of orbital period ratios. So when the period ratio comes close to some integer ratio, for example, 3:2, 4:3, 2:1, then mutual gravitational interaction between the planet can get really amplified. This is because the perturbation can accumulate over multiple periods, and the interaction is really much stronger. Yes. And this resonant interaction between the planet tend to act as a potential well that traps the planet in that resonance, while both planets are migrating towards the central star. Very good. So according to this picture, or if you ask a theorist, this migration usually produce a chain of resonance that is parked at the inner edge of the polar planetary disk. Okay. And this process can be very robust, very effective. Yeah. So many theorists believe that the initial orbital architecture of many planetary systems should be in this kind of resonant chain. But on the other hand, if you look at the mature planetary system, for example, from the Kepler sample, then most of those mature planetary systems are no longer resonant. Yeah. Only a small fraction of them are currently near resonance. Okay. And even for the near resonant ones, if you examine them closely, their pure ratio still deviate from a perfect integer ratio by about 1 to 2% level. So highlighted here in the first paragraph here. 1 to 2% deviation. So there's potentially this tension between the theory predictions that consistently generate resonant chains, and the observations that typically do not show resonance.
Okay.
People have proposed several ideas. For example, if you look at paragraph 2, some ideas include planetesimal scattering. For example, in the NEAS modeling or solar system, the leftover planetesimals slowly cause the planet to drift away from the initial orbital period. Or it can be tidal interaction with the host star. Here, the period ratio again can drift from a perfect integer ratio up to a few percent over giga-year timescale. Or it can be the dynamical interaction between the planet, for example, in secular chaos or even orbital stability, where the planet may collide with each other. In that case, you totally disrupt the initial orbital architecture.
Then it's gone. Okay, good.
So these are all some of the possibilities, but the key point here is that these dynamical evolution do take time to manifest themselves. And that usually can take several hundred million years or even giga-year time scale.
Okay.
So our insight here is if we can find a young planetary system that still records the initial orbital architecture, but before the dynamical interaction could have a chance to disrupt them.
Yeah.
And this new system, TOI 1136, is indeed one such system.
Lovely, lovely. Awesome.
Yeah. So maybe we can go to figure 1.
Let's go to figure 1, host star properties, and we have rotation period.
Yeah, so as I mentioned, the use of the system is really important. This is because we need to find a system that still records initial orbital architecture. One clue we have about the age of the system is from the host star rotation period.
Okay.
So this is a sun-like star. The T effective is about 5,800 Kelvin. And its rotation period is about 8 to 9 days.
Yeah.
And if you apply the gyrochronology relations, that puts the system at an age about 700 million years, quite similar to the Pristine cluster.
Okay.
Yeah, in this plot, you can see the star represents TOI 1136, and it's kind of on top or slightly above the Pristine sequence.
Yeah, the green ones here. Yep.
So that's one age indicator. We have a few other age indicators, including the lithium absorption as well as the chromospheric activity.
Okay.
Both of which indicate the system is at about a few hundred million years old.
Great. So there's no consistency. Great. Okay.
Yeah. Maybe we can go to figure 2 or some of the latter figures.
Sure. Figure 2, rotation periods, H and K, cluster membership, contrast.
Yeah, the contrast curve here shows that the star is a really isolated single star. We don't see any sign of companion. We also check Gaia for co-moving companion as well as the high resolution spectroscopy for eclipsing or spectroscopy binary.
Yeah. Okay.
So our best guess is this is an isolated single star,
right?
Which kind of makes sense given the very delicate orbital architecture we will see later. If the system has a companion, the gravitational influence of that companion may also cause the system to be disrupted from that initial resonant configuration.
Definitely. Very good. Cool.
Maybe the next figure.
Sure. High resolution imaging, a single star, and we have RM effect. Okay.
Yeah, I think this is the first key science result here. One thing we did is to follow up the largest planet in the system for a raster McLaughlin measurement.
Okay.
For those who are not familiar with this effect, this is basically looking at the shadow of the planet as it transits the host star. And the shadow planet sequentially covers the blue shifted versus red shifted limb of the host star, therefore breaking the balance between the two and introduce anomalous radial velocity shift. So by modeling this radial velocity shift, you can tell the trajectory of the planet around the host star. And the shape we were looking at is suggestive that the planet is well aligned with the host star rotation axis, meaning that the whole system is probably coplanar, given that we have 6 transiting planets in this system. So we know the planet are probably well aligned with each other in that edge-on configuration. Now with Rossiter McLaughlin measurement, we further know that the largest planet is well aligned with the whole star rotation axis.
Okay.
So in short, this is probably a well-aligned system in which the planetary disk is coplanar with the equator of the star. Again, that's somewhat expected. If the planetary system is misaligned with the host star, then the quadruple of the host star may also cause the planet to precess, low precession, in which case you tend to break the resonant configuration that we're seeing here.
Okay. Very cool.
All right, maybe let's go to the next figure.
Okay. Very good. I got that one. Okay, I'm with you. Big four, test observations, tests, equation, and we got some eclipse light curves. We'll take a look at all.
Yeah, so
first. Let's get a global, and then we'll zoom in as need be.
sounds good. Yeah, so I mentioned there are 6 transient planets in the system, and here is their phase field light curve. So yeah, so TESS observed this system for several campaigns, allowing us to have a decent observational baseline to discover transient planet between 4 days and 40 days.
Very
so
cool.
There can well be other planetaries, other transient planet in the system, but some of those we are not sensitive to. So at least for the interplanetary system, we know there are at least 6 transient planets.
Wow.
And for modeling the light curve, we know the radius of these planets. They range between 2 and 5 Earth radius.
Okay.
So these are the so-called sub-Neptune planets that the Kepler mission has shown us. Sub-Neptune planets are indeed the most common product of planet formation in our galaxy, with about every other sun-like star hosting at least one of these planets. It's kind of surprising that our solar system do not have sub-Neptune planets. In that sense, our solar system may be an outlier, maybe not. But that's a topic for another day, I guess.
Indeed.
Just note here, the 6 planets are indeed this very common type of product planet formation, the sub-Neptune planets.
Planet Age is kind of wild, kind of all over the place on the flux. Boom, boom, boom.
Yes. Yeah, the signal noise is not really that high, but given that we detected 6 planets and the period and the radius ratio are all consistent, we think this is quite beyond doubt a bona fide planetary system rather than some false positive scenario.
What roughly is the semi-major axis for Planet B?
Yeah, so this is the interesting point. I'll probably come back to the semi-major current semi-major axis. Yeah, so here the orbital period of the innermost planet is on 4-day orbit, and in terms of semi-major axis, it's about 5% of AU.
Yeah. Okay.
So I'll come back to why this semi-major axis is kind of significant.
Okay. Good. Good. Thank you. Very cool. Some of these look really good. Yeah. Very nice. Farthest one out a little noisy too. Okay. Very good.
Yeah, let's maybe go to the next view.
Sure. We got the priors in our analysis, stability analysis, and here we go, observe TTVs. Okay.
Yeah, so earlier mentioned that most Kepler systems are no longer resonant, and even the near resonant ones among them still show about 1 to 2% deviation from perfect resonance, where perfect resonance is a perfect integer ratio, for example, 3 to 2. So if you look at this system, QI1136, and you compute the pairwise pure ratio, this system really stands out. Their pure ratio deviates from a perfect integer ratio by about 10 to the -4 level, compared to the 1 to 2% level that we typically see for the near resonant Kepler system.
Okay.
So this tells us the system is really deep in resonance before any of the tidal interaction or some of the other dynamical effect could move the system out of the resonance.
Good.
And given the very deep resonance, it was no surprise to us we detected strong transit timing variations on all 6 planets. So for those who are not familiar with transit time variations,
Okay.
if you consider an isolated planet around a host star, then the orbit of that planet is perfectly Keplerian and the period is fixed.
Yes.
So transit should occur periodically. But now you're introducing an additional planet in the system, and the planet will interact with each other gravitationally. And now you do not have a perfect Keplerian orbit.
Right.
And if the planet are near resonance, then the interaction can be very strong, perturbing the planet. And what we typically see is that the so-called transit times, or when the planet occurs the host star,
Yes.
the timing of these events tend to change.
Right.
And by modeling how these events shift with time, we can tease out the interesting orbital dynamics that is going on in the system.
Very cool.
So shown here in the black points are the observed transit timing variations. And the red curve is our best fit.
Okay.
And the blue curves are some of the posterior random jaws.
Okay.
Yeah, so for the audience who are familiar with the transit timing variation literature, you may ask, what is the super period here?
Okay.
The super period is usually a period quantifying how fast the resonant angle completes a full cycle.
There we go.
And that usually changes as a function of orbital period. It usually scales with orbital period, but it's inversely proportional to the deviation of the planet from a perfect resonance.
Okay.
Given that the system is really deep in resonance, in other words, very small deviation, one would expect a really long super period for this system.
Yeah.
If we do the math, that's typically several decades. But here, over the time span of a few years, we do see some quasi-periodic variation in the TDV.
Excellent.
So our solution here is that the planets are not in a typical TDV solution kind of architecture. Those solutions typically have the resonant wrangles from the planet in a state of circulation. But here, we actually have a truly resonant system where the resonant angle only vibrates, or in other words, oscillate with a small amplitude around a local equilibrium.
Very cool.
And in this case, the periodicity of the TTV, or the transit time variation, is governed by the libration period. And that can be much shorter. And later we will see from modeling the resonant angle directly, the system is probably indeed in a state of true resonance, having a vibrating solution.
Very cool. Okay, I'm with you.
Maybe that's okay. Good. Maybe let's go to the next figure.
Very good. Okay, figure 6 and fractional change in the orbit delta P. Whoops. Okay.
Yeah. So, well, maybe we can show figure 6 and 7 together, since they tell the same story.
Okay.
So one thing I haven't mentioned earlier is that we have this chain of resonance, and the period ratio are 3:2, 2:1, 3:2. A very curious 7:5 second order resonance is also seen in the system compared to the other first order resonance. So by the way, the order of resonance is given by the difference between the two small integers involved. So 7 minus 5, this is the second order resonance, whereas the 3:2 or 2:1 resonance are both first order resonance.
Yes.
So if you open any textbook on selection mechanics, it'll tell you that second order resonance should be rare. First of all, the second order resonance is much weaker compared to first order resonance. They're suppressed by another factor of orbital eccentricity. And for most planets we know, the orbital eccentricity is typically a few percent level.
Yes.
So that's more than order of magnitude suppression in the interaction strength.
Okay.
Moreover, the second order resonance is much more delicate in phase space, meaning that the libration width, maybe we can, I think I do have a plot for that. Maybe we can go to that.
Sure.
Maybe some of the next figures.
Okay.
In retrospect, I should have reordered the figures.
It's all good. Figure 8?
Yeah. Maybe the next one.
Figure 8, figure 9. Here we go. The resonances.
Yeah, this one.
This one. Yeah.
Exactly this one. So,
okay.
So this one summarizes the resonance within the system. So we have planet B, C, D, E, F, G. So 6 planets. And there can be a whole host of resonant angle between the planet. For example, the neighboring pair planet form the two-body resonance, and neighboring triplets have three-body resonance, so on and so forth.
Okay.
And we examine all of this resonant angle, and the fraction in the bracket actually indicates the fraction of posterior distribution in which the particular resonant angle is in a state of libration.
Okay.
Here I want to stress again, a state of libration is the hallmark of true resonance, whereas a state of circulation means the system is just near resonance, but it's not in that true state of mean motion resonance.
Yep. Got it.
Yeah.
Cool.
So if you look at the two-body resonance angles, they have a
Okay.
really high chance of being in resonance. For example, the BC pair, CD pair, TE pair, and FT pair are almost 100%.
100%. Yeah.
And I highlighted in red the curious second order resonance in the system. Again, the pure ratio is 7 to 5 compared to the other first order resonance. And as I was mentioning, second order resonance is much weaker. And if you look at the libration width on the right, so here on the right, I'm showing the semi-major axis ratio between neighboring planets versus orbital eccentricity.
Yes.
And I've marked the width of the resonance. For example, the first order resonance 2 to 1, 3 to 2 are showing gray.
Yeah.
And the second order resonance 7 to 5, 5 to 3, 3 to 1 are showing blue.
Okay, I'm with you.
One thing you can see almost immediately is that towards low orbital eccentricity, the second order resonance is much more confined in phase space.
Yeah.
Meaning that you have to put the planet really close to being, for example, a pure ratio of 7 to 5 for the interaction for the resonant interaction to take place.
You got to be right on it.
Right on it. And imagine you're forming a pair planet in the disk. If the disk migration is fast, or if the disk migration is turbulent, then you can easily imagine a pair planet skipping the realm of influence of that second order resonance and instead got locked in a nearby first order resonance.
Okay.
So the fact that we are seeing a second order resonance really speaks about how this planetary system formed within a polar planetary disk.
Okay.
Yeah, so maybe let's go back to one plot earlier.
Sure. Figure 8. This is a big one.
Yeah, so this is a big one. So here we are showing the evolution of a resonant angle over the next century or so. So earlier I mentioned that the hallmark of true resonance is libration of resonant angle.
Yes.
And in the middle panel, we can see for a particular set of simulation, we are seeing the two-body resonant angle all librate around 180 degrees.
Yes.
So what is the significance of this libration? So I haven't touched on that. So maybe let's talk about that.
Okay.
So looking closer to home, a classic example of mean motion resonance is the Galilean moons.
Yes.
The Io, Europa, and Ganymede are in a 1 to 2 to 4 mean motion resonance state. And this was noticed by Laplace, and rightly so, it's also named Laplacian resonance.
Yes.
So the key point here is that if you write down the resonant angle between Io, Europa, and Ganymede, it also librates around 180 degrees with the amplitude very much less than 1 degree. So I won't go into the mathematical detail how you define the resonant angle. I'll just know that it is simply the generalized coordinate for the resonant part of a Hamiltonian, and captures both the orientation and orbital phase between neighboring planets. So if you look at Io, Europa, and Ganymede, the libration of the resonant angle actually detects there's no triple conjunction between the satellites.
Right.
So whenever two satellites have a conjunction, the libration of the resonant angle ensures that the third satellite is far away, at either 90 degrees or 180 degrees away.
There you go. Yes.
So the avoidance of triple conjunction helps to avoid chaotic interaction between the satellites, and in turn promote the long-term orbital stability of the whole system. So coming back to planetary system, well, we are looking at this case of TOI 1136, and again, we see this libration around 180 degrees.
Yes.
And again, this libration ensures the
Very
planets are maximally separated
Yeah, very cool.
in the phase space so that they
Uh-huh.
minimize the chaotic interaction between the planets and promotes the long-term stability.
Very cool.
So in this plot, something I should mention is that according to our TDV solution, the system can adopt to different kind of architecture. The first architecture is when the planets are maximally separated from each other. This is showing the top middle panel here. Here, the dotted line shows the argument of pericenter between each planet. And you can see for neighboring planets, the argument of pericenter are diametrically opposite each other, more or less. So having this configuration means that whenever the planet are close to the star, they are also separated far from each other.
Right.
So this tends to minimize the interaction.
Correct.
And in this kind of configuration, if we integrate the system over time and see their resonant angle, they are indeed in that state of libration, as shown in the middle panel here.
Okay.
But some of the other posterior solution, although a small fraction of them, in this case, the planets are not maximally separated from each other. This is shown on the top right panel. Here you can see the argument of the pericenter is kind of random. Sometimes they even align between
Yes. Right here, there.
So in this, we believe this is some of the random solutions that really do not capture what is going on in the system, given the lack of data, lack of constraint we have currently. And this is a very high dimensional problem. So just sampling the phase space randomly, we are bound to sometimes end up with this somewhat unphysical solution. In this case, the resonant angle, as shown in the bottom panel, the resonant angle evolution can be kind of chaotic. You can see some of the planets are librating, but in gray color, particularly the second order resonant planet pair E and F, you can see the resonant angle changes from a state of libration to a state of circulation, where the resonant angle explores the full 360-degree range.
Indeed.
We don't think this is going on in the real system. It is just an artifact of the limited data coverage we have, that we haven't been able to pin down the system to the true island of stability that they have in the phase space.
Okay.
So with more data, hopefully we'll be able to eliminate this kind of solution.
Cool.
Yeah. So on that note, maybe we can go back to one figure earlier, figure 7.
Sure. Figure 7. And we have, oh, here we go. Yes, we punted on this one. Okay.
Yeah, so it's mentioning that planet E and F are the second order resonance, and this does appear to be the weakest link of this resonant chain. Okay. Remember, the other links are all first order resonance.
Yeah.
So if we integrate the system over time, then planet E and F are by far the most likely to break away from resonance first. So this pie chart shows a fraction of the system in which the particular planet break away from resonance first. So the system is so dynamically packed that once a planet break away from resonance, the orbital instability quickly follows. For example, there can be collision between the planet, or some of the planet may be scattered out of the system.
Right. No, you've lost.
So yeah, so again, this pie chart shows the planet E and F, which are the planet we expected, which are the weakest link of the resonant chain. And if we just integrate over time, indeed they appear to be the first system to break away from resonance.
Right, right.
Cool. All right, good. Let's maybe move on to some of the later figures.
Very nice. Okay, figure 8, figure 9, we already covered. That's our ladder resonances, so to speak.
Yeah, exactly.
And then how about the simulations on the migration?
Right. So I think this is perhaps the money plot of the paper here. So earlier mentioned, you can form a resonant chain from this migration, but so far, well, we do not know how that occurs in detail. So TOI 1136 is, as I mentioned earlier, is a pristine case of resonant configuration where the planets are still very deep in resonance. And we have seen the various resonant angle indeed in a state of libration rather than in a state of circulation. So we're very confident the system is indeed a well-preserved, or in other words, a fossilized resonant chain that was produced by this migration before dynamical interaction could modify it.
Cool.
So
Okay.
using the observed orbital architecture, we can investigate how planet formation occurred, or planet formation including planet migration occurred in the system.
Okay.
So what we did here is try to reproduce a TOI 1136 by forming them in the disk while turning on this migration.
Okay.
So here we explore three different prescriptions for how that migration occurs.
Okay.
In the first column on the left, we're migrating all the planet in a polar parent disk, turning on type 1 migration on all the planets simultaneously.
Yes.
And one key thing we have in the setup is we also putting an inner edge of the disk. If you look at on the left here, the inner edge is produced by the truncation of the disk due to the magnetosphere of the host star.
Okay. All right.
As a disk expert, this is probably a prominent way in which the disk is truncated. Here, the magnetic interaction with the host star is so strong that it start to outweigh.
Yeah, it's moving out here. You know, let me zoom in on that just a little bit. Yep. So here's our magnetosphere, and we're pushing this one out, and everybody else is in. Yep.
Yeah. So the key thing here is that having the inner edge, you will start to introduce a pressure bump to the disk. So having a pressure bump means that usually the disk density increases towards the inner disk. By having a disk bump, you suddenly have to drop the density back down to zero at some point. So you introduce this reversal of the disk density versus semi-major axis. And if you put in that reversed gradient of the disk density versus semi-major axis into a disk migration simulation, the result you will see is that the direction of the migration is actually reversed. So earlier I mentioned that in most part of the disk, the migration is towards the host star. But within the pressure bump, you can have migration away from the host star.
Yes.
This setup is crucial because without the inner disk, you can imagine all the planets will just keep on migrating to their host star until they plunge onto their host star.
Yeah.
So having the disk edge is really instrumental for reversing the direction of the migration. Moreover, the change of the migration direction also tend to slow down the overall migration rate. You can imagine like the planets are like children holding hand, and you're pulling on one children, the other one had to move with the first one. Now you're pushing the first kid, then the other children have to stall at some point.
That's a great analogy. Very good. Very good. I love it.
So that's one thing we try. One of the prescriptions we tried. The other prescription is showing the middle panel. Here, the migration is only applied. Here the migration is only applied to only the outermost planet. And on face value, this can seem somewhat contrived. Why would you migrate only one planet, not the other? One possibility is that when the disk is starting to dissipate, and people have been seeing, for example, using ALMA observation, their transitional disk, where the inner disk had already dissipated due to a combination of, for example, Foley vibration or magnetic wind from the disk. So it is possible that the disk can only be around a subset of the planet. And the reason why we set up this prescription is that it is actually widely used in the literature to produce resonant chain. By only moving one planet, you're ensuring that migration is slow. Typically, the other planet migrates slower. And moreover, the interaction, the encounter between the planets are all convergent. So something I haven't mentioned is that in order for planet to be captured into resonance, the interaction or the encounter between the planet have to be convergent. In other words, the pure ratio decreases over time rather than increase. It's just how the phase space morphology is that you have to capture the planet in this way for the resonant interaction to operate.
Okay, great, thank you.
Yeah, so in the second prescription, you're only moving one planet. So you're ensuring all the encounters are convergent. And this way, it really helps to capture the system into resonance.
Okay, good.
So the final prescription shown on the right is very similar to the first prescription, but the only difference is that we allowed a large-scale migration for the planet. So we launch all the planets beyond 1U, where people have been arguing whether the sub-Neptune planet that Kepler discovered are the formation or the product of in-situ formation, which they form on the orbits more or less close to the orbit we see them today, well within 1U. Or maybe they form further out beyond the water snow line.
Right.
In which case, the planetesimals are covered in icy mantles, and in that case, the planetesimal can more likely stick with each other and promote the growth of the planetesimal to planet embryos.
Okay.
So that last prescription tests this ex-situ formation scenario in which the planet formed beyond 1U before migrating inside.
So there, right. Okay, very good. I got it.
So I guess we have a bunch of other plot. I don't have time to explain in detail. Let me just say that the prescription that works best is actually the first one.
Okay.
In which case, we can form a multitude of analogs of QI 1136, which is shown by the blue points here. Okay. Here, the planet migration can be slow enough. In other words, the various planets can click into the resonance we are seeing, including that second order resonance. Okay. Again, the second order resonance is really weak and is really confined in phase space. And you have to migrate the planet slow enough so that the planet feels the second order resonance and get there.
Right, right. Okay, very good. I got it.
Yeah, in the contrasting case of the large scale migration, in order for the planet to migrate within the 3 million year disk lifetime, the migration is necessarily fast. And in that case, we don't see a lot of system in second order resonance.
Right, got it.
And in the middle case, we're only moving one planet. Here, the issue is that we do not deposit the planet deep enough into the resonance. If you look at the last panel here, here the x-axis is actually deviation from perfect resonance.
Right.
In this case, what we are seeing is that in order to deposit the system deep in resonance at 10 to the -4 level, we need to invoke the first prescription, in which we reverse the torque on the planet due to the pressure block. And there it helps to deposit the planet deeper into resonance.
Yeah, okay. Yeah, that's very important, actually. Okay.
Yeah, so
cool. Got it.
Let's move on to some of the later figures.
Okay. I like the shot. That's the money shot. Big 10. Figure 11, we got some migrations.
Yeah, so here we are showing, maybe I should go through this briefly. So here we are showing a typical time evolution of a system that eventually gets locked into the observed resonance. The first panel shows the deviation from perfect resonance. Delta. So we started the planet pair just 2% away from resonance. Yes. And you can see over a time scale of maybe 100 kiloyears, the planet can click into resonance, and now they're almost pinpoint on the integer ratio. Got it. Second panel shows eccentricity. Here, I want to point out that planet, although the planet started out on perfectly circular orbit, but their mutual interaction is amplified when they are locked into resonance. And in that case, the mutual interaction can force a non-zero eccentricity on the planet. Definitely. All of them. So the third and fourth panel shows the time evolution of some of the two-body and three-body resonant angle. And you can see the system started in the circulation case, where the resonant will explore the full 360-degree range.
Oh,
But
that's-
once they are captured into resonance, they actually librate close to 180 degrees.
That's
In
wild.
a few cases, the libration is shifted away from 180 degrees. This is a well-known effect for 2-to-1 resonance. I won't go into the depth of that. For most cases, the libration is indeed around 180 degrees.
Yeah, most.
Yeah, maybe let's move on to the next figure.
Those are nice, very nice. I think it's totally wild. It explores the whole range. Okay,
Yeah.
12 properties of the disk.
Yeah, so one key result from our work is that if we leverage the disk migration simulation we ran, we can actually put some constraint on the properties of the disk that form TOI 1136.
Right.
So the plot on the left shows the overall disk density at 1 AU in units of gram per centimeter squared.
Okay.
And the y-axis is the aspect ratio of the disk, namely the scale height of the disk versus the radius.
Got it. Okay.
Yeah, the blue points are successful simulations, and the vertical cyan line actually is the minimum mass solar nebula, which is our best understanding of the disk for the solar system.
Right.
So for the solar system, the number of people usually quote is about 200 gram per centimeter squared at about 1 AU.
Yes.
You can see for TOI 1136, all the successful simulations have a density lower than that.
Yes.
Typically less than 1,000 grams per centimeter, per square centimeter.
Yes.
So again, this is useful. The low density is useful for slowing down the migration rate and allowing the planets, including the second order resonance, to be formed during this migration.
Cool. So it's consistent. Very good.
Yeah. Yeah, maybe let's skip the other panel and go to the next figure.
Okay. Figure 13 and time evolution and deviation. Delta.
Yeah, so
Yeah.
one other thing we investigated is how the system would evolve over time.
Right.
So earlier I mentioned that most mature Kepler systems are no longer resonant. And even the near resonant ones still show about 1 to 2% deviation. One key way we can generate that deviation is through tidal interaction with the host star.
Sure.
So here, remember, when the system is in resonance, the neutral gravitational interaction between the planet can constantly pump a non-zero eccentricity for the innermost planet. This is we have seen that during the evolution plot. So having a non-zero eccentricity of the planet again turns down the eccentricity tide between the planet and the host star, and the eccentricity tide is going to dissipate, cause a lot of dissipation on the planet.
Yes.
So if you calculate the evolution of the system, one key prediction from those calculations is that if the planet continues to tidally interact with host star through eccentricity tide, then the P ratio between the neighboring planet will start to deviate from that perfect integer ratio.
Right.
And time behavior from those calculations is typically time raised to the 1/3 power. So the x-axis here is indeed time.
Sure.
In that sense. And the y-axis is the deviation delta from perfect resonance.
Perfect resonance, yes. Okay.
And you can see this theoretical behavior is very well covered in this direct embodied simulation. We can see the various planet pair from planet pair BC to FG indeed follows more or less a linear trend in time.
Yes.
So earlier we know the system is really deep in resonance at about 10 to the -4 level. So one exercise one can do is compare the currently observed depths of resonance from the time evolution, the expected time evolution. And we know the age of the system. We know the currently measured resonance depth and the expected rate of deviation from resonance. And that rate in turn depends on the tidal quality factor of the planet.
Yeah.
So by combining the three effects, we can actually put some constraint on the tidal quality of the planet.
Cool.
Given that the system is 700 million years and still very deep, very much deep in resonance, the tidal dissipation on the innermost planet is probably quite weak.
Okay.
So won't go into the detail, but the bottom line is that for this planet, the tidal quality factor is probably similar to our Neptune, typically at 10 to the 4 or 10 to the 5 level.
Okay.
In contrast, if that innermost planet, by the way, that innermost planet is about 2 Earth radius. If that planet is a rocky planet, similar to our Earth or the other terrestrial planet, in which case the rheology as well as the ocean, surface ocean on Earth can greatly amplify the tidal dissipation. For example, on Earth, we know our shallow Earth coupled with the Gulf, at various geographical locations, actually greatly amplify the tidal dissipation on Earth. Our Earth has tidal quality factor on the range of 10 to 100 level, which is much faster compared to the Neptune-sized planet.
Yes.
So for QI 36, we think the innermost planet at about 2 Earth radius resembles a Neptune more rather than a super Earth or the terrestrial.
Yeah. Okay. Cool. Very nice.
Let's move on to the next plot.
And 14, we're going to do some deviations.
Maybe let's skip this one. I think I already covered it.
And we got more deviations, and then we got
yeah. So
B.
maybe in retrospect, maybe we should have started with this plot. This plot really puts the system in perspective. So the top left shows the deviation from perfect resonance, and I've been talking about that 1 to 2% deviation from the near resonance.
Right.
It's shown by the blue histogram.
Yeah, very cool.
This system is right on top of origin, shown by the vertical red line.
Right.
So these are really deep in resonance.
Indeed, they are. Okay.
Yeah, let's move on.
Okay, 16. Mass and radius, properties of planets. 17, mass and radii. Ooh, and compositions.
Yeah, so these are the 6 planets from the system, and the radius of the planet came from the transit depth, and the mass of the planet came from the analysis of the transit timing variation. In other words, the mutual gravitational interaction between the planets. And the planets are between 2 and 5 Earth radius, and the mass is between 3 and 10 Earth mass, 3 and about 8 Earth mass.
Yes. Okay.
I will go through all the planets. Let's just highlight planet B. Earlier mentioned that from the rate of deviation from perfect resonance, we have known that the tidal dissipation on planet B is rather weak.
Okay.
And again, if you look at the composition of this planet on mass radius diagram, planet B is 2 Earth radius and 3 Earth mass, and it's right on top of 100% water world.
Wow.
Or it could be about. It can also be the case that the planet has the Earth-like core, but some hydrogen helium envelope. That is shown by the magenta line.
Yes. Okay. Okay.
In other case, the planet is probably not a bare rocky core like some of the terrestrial planets we have seen.
Right.
It's more likely covered in a thick ocean layer or some thick atmosphere.
Okay.
In that case, the dissipation is much more suppressed compared to a rocky planet with, say, a shallow ocean.
Wow.
So just making the link between the dynamical simulation we did versus the measured mass radius of this planet. So things check out.
Very cool. We got some consistency there. Water world. Water worlds. All right.
Well, I'm not sure it's a water world yet, but future observation.
Understood. Raw speculation on my part. 18. Right, here we got the big system. The broader picture.
Right. So the final schematic here tries to put the system into perspective. So earlier we mentioned that if you ask the disk migration people, they'll tell you that resonant chains should be common. It's robustly produced by disk migration. On the other hand, if you ask Kepler expert, they will tell you that the observed orbital architecture of the mature planetary system are no longer resonant. Our solar system, well, for the planets, most of the planets are non-resonant, except for example, Neptune and the trans-Neptune object.
Yeah.
So I can't help but speculate how TY 1136 and our solar system compare in terms of formation pathway.
Okay.
So earlier we mentioned that the disk migration really requires the planet to grow to a critical size so that its gravitational influence becomes important on the disk. And that critical size, depending on the disk, probably can be, say, for example, Mars mass or even larger.
Okay.
So for TY 1136, our speculation is that the planetary cores probably grow pretty rapidly when the disk was still around. So that the various planets grow to the critical size and they start to back react on the nascent disk, and the planets start to migrate on the type 1 migration.
Okay.
And that migration really helped in locking the system into a resonant chain.
Yeah.
On the other hand, for our solar system, one might speculate that the growth of planetary core was probably suppressed, so that the planet didn't reach a critical size to start migrating. So our terrestrial planet probably remain non-resonant in the chain, and they have to be fully assembled after the disk dissipated in the classical giant impact phase.
Right.
So why is the case that our terrestrial planet didn't grow so fast?
Yes.
Okay. If you ask the solar system people, they will tell you that a prominent theory is the Grand Tag model, in which our Jupiter and Saturn formed early, and Jupiter initially formed around 3.5 AU.
Yes.
And once the two planets interact in so-called type 2 migration, the two giant planets actually moved inward all the way to about 1.5 AU before moving out again. Yes. So in that case, the early formation of the giant planet in our solar system and their inward migration was probably pretty disruptive to the growth of our terrestrial planet, limiting the size within the disk. So our terrestrial planet maybe didn't grow to the critical size, and they probably remain non-resonant.
Okay.
Yeah, so TY 1136 is probably one of the very first fossilized resonant chain. There is observation. The system is still very deep in resonance, and does tell us, at least for a subset of planetary system, this migration indeed played an important role in shaping the initial orbital architecture of a planetary system. So how does a resonant system evolve over time? So this is shown by the bottom 3 panel here. Here, if you look at the rightmost panel, here, if you look at the majority of Kepler system, they are not resonant. And it could be the case that these planets started out similar to our solar system. They didn't have the resonance to begin with. Or it could be the case that orbital instability between the planet or giant impact collision between the planet totally disrupt the initial orbital architecture. So we no longer see a resonance. So this is the vast majority of the mature planetary system. So far, we know about 1,000 of them, and then 90% of them are in this non-resonant configuration.
Okay.
About 10% of the mature planet system fall in the middle column here. Here, the planets are close to resonance, but not perfectly so. Their P ratio deviate from resonance at about 1 to 2% level, highlighted by the green, the red box here.
Yes.
So here, these near resonant systems, if you analyze them closely, their resonant angle is actually in a state of circulation rather than libration. Yes. So one may argue that these are just near resonant instead of being truly resonant. And there are various ways a planet can break from resonance. At the start of the talk here, we mentioned planetesimal scattering, tidal ingression, or some other processes.
Yes.
So these are the mature systems that have undergone some of those dynamical evolution, moved sufficiently off resonance and break away from it. And today we see these systems are circulating transit timing variations.
Yes, cool.
Previous work, for example, Sam Haddon and Joran Lithwick in 2017
Yes.
analyze the system as a population.
Mm-hmm. Mm-hmm.
So finally, if a resonance system is really lucky, escape the fate of giant impact collision. Moreover, the tidal interaction with the host star is weak, as we have seen for QI 1136, then the system can remain truly resonant over many gigayear timescale.
That's wild.
In this case, we see the system as a true resonant chain.
Yeah.
And this system is very rare. So far, we only know about 10 examples of those, including QI 1136, Kepler 223, and the very famous TRAPPIST-1 system is another. Yes. So yeah, so these are the really lucky systems that managed to hold on to their initial orbital architecture.
Cool.
Yeah, so with that, I think that's pretty much the gist of the paper. Frank, I don't know if that was clear. Do you have any questions?
Oh, that was totally awesome. Yeah, I followed you. No, it was great. And just so people know, there's this very lovely appendix that takes care of some of the gritty details, as we say. So do check it out. It's very cool. It's a lovely paper. All righty. Well, that was very awesome. And Fei, I want to thank you so much again for walking us through your very lovely article. Thanks.
Thank you, Frank. Be happy to.
You mentioned it a couple of times as we went through, or you hinted at it, shall we say, as we go through. So let me push on it a little bit. Where do you think we go over, let's say, the next 2 to 5 years on this topic? Are there additional observations to do on this specific system? Perhaps at other wavelengths might be able to pull something out?
Yeah.
Or is there more depth going into some of the other 10 systems that are known, TRAPPIST, for example, et cetera? Are there additional hunts to maybe find 100 of these over the current 10? And just sort of, where do we go over the next couple of years on this topic?
Yeah, definitely. So one frontier is definitely the young planetary system. As we have seen for QI 1136, its age being 700 million years is really crucial in preserving that initial orbital architecture.
Yeah.
It'd be nice if we can discover additional system with similar age or even younger. For example, we know the typical disk lifetime is 3 million years. If we can discover the system, say, on 10 million years timescale, then we know, indeed, that system was already formed during this migration, rather than some other processes that can take hundreds of million years.
Okay.
Another area we can make progress is that we mentioned that the system probably migrated from further down in the disk. And in this paper, our best explanation is for short range migration.
Yes.
Where the migration is slow so that the planet captures into the second order resonance.
Mm-hmm.
It could be the case that the migration rate evolves with the disk. So initially the disk may be pretty dense. So migration happens pretty quickly, moving all the system from beyond, say, the snow line to the inner disk. But the migration rate turned into a slow state when the disk was starting to dissipate, allowing them to capture into the delicate resonance. Mm-hmm. So if this is true, then the planet may have formed further out in the disk, where we should expect to see a lot more volatiles or other signatures, for example, carbon to oxygen ratio, which changes significantly within or beyond the snow line. So with JWST, one can take a look at the composition of the atmosphere and start to place some constraint on, for example, the C2 formation of the atmosphere, and shed light on where exactly these planets form.
Nice.
Another area, as you mentioned, is water world. The inner planet here is kind of consistent with a sub-Neptune having hydrogen helium envelope, or a terrestrial planet with a thick ocean layer.
Yeah.
And people have been claiming that water world have been seen around other systems, but so far there's no smoking gun evidence for those.
Okay.
Again, this is where JWST observation can shine.
Very cool.
In cycle 2, I'm sure there are plenty of proposals looking at potential water world and see if their atmosphere does hold up to that claim.
Right. Very cool. Very cool. I think it's going to be very awesome watching this develop over the next couple of years as we further characterize these delicate systems and perhaps find some new ones, even younger. We can say something about that. Be very cool. Very nice. Very nice. Fei, I want to thank you so much once again for walking us through your article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
You're welcome.